How's it going, guys? Today we're going to talk more about definite integrals, and we're going to do the two exploration problems from your book. So if you didn't bring your book home yesterday, um, that's okay. I've got the problems for the explorations written in the OneNote. If you're not able to do the homework because you didn't bring your book home, send me an email. Anyway, so the exploration problems, the first one says, given that the integral of sine of x with respect to x from 0 to pi is equal to 2, find the value of the following integrals and give your reasoning. So the first thing that I want you guys to do is just pause the video and look at each of the graphs that are provided and try to figure out which graph goes with which problem. Let me give you an example. The first graph, or the first problem, is sine of x, so we're looking for a graph of sine, and the integral goes from pi to 2 pi. So we're looking for a place where the shaded region, which would be the representation of the integral as an area, goes from pi to 2 pi. If we look at this first graph, we can see it's graphed from negative 2 pi to 2 pi. So each of these notches is pi over 2. This is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. So it looks like this first graph is graphed from pi to 2 pi. So this graph goes with question 1. So again, I'd like for you to pause the video, match each of the graphs to each of the problems, and then resume the video. Alright, so let's check your answers. So we know the first problem goes with the first graph. The second problem is also sine x, but the integral goes from 0 to 2 pi. So we're looking for something that goes from 0 to 2 pi, and that looks like that is the graph right there. And number 3 goes from 0 to pi over 2. So that looks like that is this graph in the corner here. Number 4 is a graph of sine of x plus 2. So we're looking for a graph that's shifted vertically by 2. And it looks like it's this graph down here at the bottom. For number 5, we're looking for a graph that's twice as tall as sine of x. And if we're looking, let's see, yep, this last one here is twice as tall, since it comes up to a value of 2 instead of 1. Number 6 is sine of x graph from negative pi to positive pi. Looks like that's right there. Problem 7 is a graph of sine of x over 2 from 0 to 2 pi. So one way we can think of this graph is that this is a graph that waves more slowly than the other graphs. Or we could plug in the values of 0 and 2 pi and think of what the values should be. Normally, sine has a value of 0 at 0 and a value of 0 at 2 pi. In this case, but it would have gone through a complete oscillation. So we would have waved, like in this graph here, we would have waved up and then waved down between 0 and 2 pi. So if we're waving half as slowly, then we should be going from 0 to 0, but only complete the top half of that arc. So the graph is right there. We can see we're waving up and down to 0, but not the complete up and down. So it's waving half as fast. The last graph is actually a graph of cosine, and it's the integral from 0 to pi. And we know that cosine starts at 1 when cosine is 0. So that is the last graph left. Now that we've matched all of the graphs to their corresponding problem, we can use the given information to try to determine what the value of each of the areas is. So for the first graph, if we're looking at the value of sine of x, the given function, the value of sine of x from 0 to pi, this is sine graph from 0 to 2 pi. So from 0 to pi, they're telling us that that area is 2. So if we look at the graph of sine of x from pi to 2 pi, we can see we have that same shape, but it's under the x-axis. So the area is -2. It's the same value as we were given for the integral of sine from 0 to pi, but since it's under the x-axis, it has a negative value. So let's look at the second graph, the integral of sine x from 0 to 2 pi. Here we can see we have the same amount of area above and below the x-axis. So that's going to add to 0. It'll end up being 2 plus -2. The next graph is sine of x integrated from 0 to pi over 2. And if we look here, this is exactly half of the area of the example problem. And so we could guess that the area is 1. Next, we have the integral from 0 to pi of sine x plus 2. This one's a little bit tougher, trickier, but if we split up the region, we can see that actually what we have is the given region, which has an area of 2 sitting on top of a rectangle, which is going to have, if we're integrating from 0 to pi, and we know that we shifted our sine curve up a value 2, that means this rectangle has a height of 2 and a width of pi. So we could guess that our answer is going to be the area of the rectangle, which is 2 pi, plus the area under the sine curve, which is 2. Our next question is question 5. We have the integral from 0 to pi of the function 2 sine x. In this case, one way to think about this is all of our Riemann sum triangles are twice as tall as they would have been before, because the function is being multiplied by 2. And so if the original function gave us an area of 2, this new function gives us an area of 4, twice as much. The next problem is the integral of sine x from -pi to pi, and that was here. And again, we can see we have the same amount of area above and below the x-axis. And so the value is 0. For the integral of sine of x over 2 from 0 to 2 pi, so here we can think of the same Riemann sum rectangles, except these rectangles, just like the graph, are going to be stretched out to be twice as wide as they were before, since our new interval is, instead of being from 0 to pi, is now 0 to 2 pi. Each of those rectangles is going to be twice as wide. So our area is going to be twice what the original area was. In the last question, we have cosine x from 0 to pi, and that was right here. And again, we can see we have the same area above and below the x-axis, so that's going to be 0. Let's move on to exploration 2. In this question, we're given a function f of x is x squared minus 4 divided by the quantity x minus 2. And they want to know if the function is integrable over the interval 0 to 3, and if so, use the method of areas to try to figure out what the answer is to evaluate the integral from 0 to 3 of the function with respect to x. So let's look at why this function might not behave as nicely as we would expect. So the function itself, x squared minus 4 over x minus 2, on the interval 0 to 3 has a discontinuity. X is not allowed to be equal to 2 because that would cause division by 0. So one of the things that we can check is what type of discontinuity is this? Especially with rational expressions of polynomials, we should check to see if it's a removable discontinuity. In this case, it is. If we factor the top, we'll have x plus 2 and x minus 2. The bottom is x minus 2. So the discontinuity is removable, and our extended function is x plus 2. So the question, is the function integrable over the interval, is a little bit interesting, and there's a bit of peculiarity to the way the function behaves. So let's look. So in this case, the function that we're graphing has a y-intercept of 2, goes up to some value at x equals 3. And at x equals 2, it has a removable discontinuity. So if we were to integrate this function, that would be a representation of the area under the curve. And so if our integral was from 0 to 2, or 0 to just before 2, then it would be this area here. And if our integral was from just after 2 to 3, it would be the area here. So the idea is that the only area that we're missing is this very small slice, this very, very tiny rectangle that represents when x is equal to 2. And the dimensions of that rectangle would be, if we use our extended function, the rectangle would be 4 high and have a width, delta x, that is very close to 0. Since the function isn't discontinuous from 2 to 2.1, it's not discontinuous from 2 to 2.01, it's only discontinuous at 2. And 1 point doesn't make a line, so there really isn't any length or horizontal interval there with respect to that discontinuity. It's just 1 point. So in reality, the area that we're missing from this little tiny rectangle due to the point discontinuity is basically 0. And the function is integrable over the interval, even though it has a discontinuity. And the integral from 0 to 3 of x squared minus 4 over x plus 2 dx is basically the same as the integral from 0 to 3 of x plus 2 dx. And we can estimate that area by looking at the dimensions of the shape.